Page 9 of trig functions, equations, and identities, addendum. This is the page or the 2 pages that we save for later because they use math induction, which is covered in chapter 12, which we just did. So let's take a look at the questions here. So first it asks us to give an example of a trigonometric series. So remember, a series is a sequence that's added together. So it would look something like, okay, sine of x plus sine of 3x plus sine of 5x plus dot, dot, dot. So anything like that, a pattern of trig functions that are added together. Give an example of a trigonometric product. So this would be like if you have a sequence of trig functions that are multiplied together, kind of like that. Okay. Remember that sometimes series that are added together are represented by a sigma for some, and product is represented by pi as a product. And then they put the relevant counters here, like 1 to infinity or whatever. Okay, let's do number 1. We are going to simplify this trigonometric sum here, a series. Okay. 1 plus sine squared plus sine cubed plus sine to the fourth plus blah, 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 all the way to the sine to the n minus 1. It might be a little hard to see how this could be simplified, but remember that I could represent this as I could substitute in, instead of sine x, I could just put a variable like r or constant, and I could put 1 plus r squared plus r cubed plus r to the fourth plus dot, dot, dot. And does that look familiar? This is a certain kind of series, one that we learned earlier. We only know geometric or arithmetic series. This one is a multiplying always by r, so it must be a geometric series, right? So yeah, this is a geometric series, and the multiplier is r, and r happens to be sine x. And what would a be in this case, a or u1? It would be the first term of the sequence, which is 1. So do you remember the sum of a geometric series? It can be expressed as a, or u1, over 1 minus r. So in this case, I could say that it is, I'm sorry, that's if you have an infinite series, and in this case it's not infinite, it's finite. Okay? So on the top I have u1, which is 1. I have 1 minus r to the n, which would be sine to the, it says the last exponent here is n minus 1. So the last term is the nth term. So that would be sine to the n of x. And on the bottom, I'll have 1 minus sine of x. Now, instead of to the n minus 1, sine of n minus 1, which is the nth term, they want us to find the sum of the infinite series. And the sum of the infinite series formula is similar to the sum of the nth up to the nth term formula. It's actually easier. It's u1 times, or u1 over 1 minus r. Isn't that easy? So we're going to have u1, which is 1, and 1 minus sine x, which is 1 minus r. And that's it for B. what is A or C? Find the value of x, which is an element between 0 and 2 pi, such that the series in B has a sum of 2/3. Sum of 2/3. Okay, so let's see. If we want B to have a sum of 2/3, let's just set B equal to 2/3, and then we'll solve for x. Okay, so we got that, and now let's cross multiply to get the x out of the denominator. So 3 equals 2 times 1 minus sine of x. Let's isolate the x now. We'll divide both sides by 2. 3 halves equals 1 minus sine of x. Let's put x on sine of x on the left to make it positive, and let's subtract negative or 3 halves from both sides. We'll get negative 1/2. So sine of x equals negative 1/2. When does sine of x equal to negative 1/2? That would be, looking at the unit circle, this angle and this angle, right? Negative 1/2 is the sine of these two angles. So it would be 180 plus 30, that would be 210 degrees. And it would be 360 minus 30, which is 330 degrees. And if I was to put that in radians, it would be pi plus 1/6 pi, which would be 4/6 pi. Would that be 4/6 2/3 pi? 2/3 pi. And the other one would be 12/6 pi minus 1. It would be 11/6 pi. No, I think this one here is wrong. It's 1 pi plus pi over 6. That would be 7/6 pi. Okay, so those are the two values of x between 0 and 2 pi, which would make sine of x negative 1/2, which would make the sum 2/3. Okay, anything else on this one? Nope, that was it for 1. Let's do 3. From sine of 2x equals 2 sine cosine, we observe that sine cosine equals this, which is equal to this. Prove that sine times cosine of 2x is equal to this. Okay, the first thing that I see on this left side, which is suspicious, is sine times cosine, right? Sine times cosine is related to sine of 2x. What if we take sine of cosine? Let's see, if we put sine and cosine by itself, then that should give us sine of 2x divided by 2. And then we're going to substitute it in there. So we'll get sine of 2x divided by 2 cosine 2x equals, and in this case, we know that 2 sine 2x cosine 2x is equal to sine of 4x, right? If you have a double angle, you can do 2 times the sine of the single angle times the cosine of the single angle. So we can take sine 2x times cosine 2x divided by 2 and divide the other side by 2, and we'll end up that sine 2x cosine 2x is equal to sine 4x divided by 2. So let's do that substitution. We'll take sine 2x cosine 2x and we'll substitute in sine of 4x divided by 2, and there's still this 2 here, so there's another 2 here. So that would be sine of 4x divided by 4 could also be written as sine of 2 squared x divided by 2 squared, which is exactly what we want, right? All right, let's shrink this down. Okay, let's look at the next one. Now they want us to prove that sine cosine 2x, cosine 4x is equal to this. So let's try that. Okay, so we know that sine cosine is equal to sine 2x divided by 2. So let's substitute that in. Sine 2x divided by 2 times cosine 2x times cosine 4x. So we could put sine 2x, cosine 2x together into a expression with sine 4x with this identity right here, right? So let's do that. We're going to put sine of 4x divided by 2, which would be sine of 4x divided by 4, including that. So we'll have sine of 4x divided by 4 cosine of 4x. Okay, and that we could rewrite as sine of 8x divided by 2 times the 4 that was already here. So that would be sine of 8x divided by 8. And we could rewrite that as sine of 2 cubed x divided by 2 cubed. And we've proven that too. Okay. B, assuming the pattern in A continues, simplify this. Okay, and then simplify this. Okay, so let's try to see the pattern here in the first one. So we have, in the first one we had a 2 here, and then we end up having a 2 there and 2 there, right? Here we have a 4 here, right? And then we have a 3 and a 3 there. And in the first one, we have a 1 here. We have a 1 and a 1 there. So it looks like we can count the cosines, right? If we count the cosines, there's 3 cosines here, then we'll have a power of 3 there. If we count the cosines, there's 2 there, we'll have a 2 there. If we count the cosines, we count 1 there, then we have a 1 there, okay? So let's look at the ones they gave us below. There is 1, 2, 3, 4 cosines. So what we would expect is that B1 would simplify to the sine of 2 to the 4th x divided by 2 to the 4th, right? What about the next one? The next one has how many cosines? We have to write them out because they left a whole bunch out here, see? So there would be cosine of x, there'd be cosine of 2x, there'd be cosine of 4x, there'd be cosine of 6x, 8x, sorry, and cosine of 16x, and cosine of 32x. So how many cosines is that? 1, 2, 3, 4, 5, 6 cosines. So then our expression is going to be sine of 2 to the 6x divided by 2 to the 6th. Just notice that my 2 to the 4th looks a lot like 24. Okay, that's it.